Well, thank you for inviting me, and I'm delighted to speak here at St. Thomas. And it's a wonderful opportunity to communicate with you guys. I have an ocean orientation. I've been a practicing oceanographer for about 45 years at the doctoral level, and I was interested in the ocean since I can remember. So I'm here to tell you a bit about how the ocean plays a role in climate change. And it's one that isn't very much talked about. We saw a very good presentation about the scientific basis for the hockey stick showing the increase in global surface temperature since basically colonial times. And that's certainly the case. And it turns out that the ocean is communicating with the atmosphere. There is heat exchange that goes between them. And it's not a very efficient process because in many cases the ocean is colder than the overlying atmosphere. So when you heat up the surface layer, it resists vertical mixing. And so it's taken a long time to get the heat into the ocean, but that is something that is essentially occurring. In fact, according to the IPCC, over 93% of the heat of global warming that's in the Earth system today during the last 70 years, since 1970 I should say, has resided in the ocean. So in a very real sense, global warming has become an oceanic phenomenon. Clearly the atmosphere plays a role in the heat getting to the ocean, but the ocean is the great storehouse, the thermal flywheel of the world. And so it happens that as the ocean warms up, we have atmospheric transport of heat, and mostly in the form of latent heat, and we have oceanic transport by means of strong ocean currents, which essentially circulate water around the Earth in very large quantities, and part of that circulation is bringing warm, salty water to the Arctic, and the Arctic sea ice is beginning to rapidly melt and disappear. Iceberg output in the major Greenland glaciers and also Antarctic glaciers is accelerating, as well as meltwater. And so a number of glaciers, major glaciers that deepen inward under the ice sheet are begun to melt in ways that will be very difficult to stop. So the heat that's been put in the ocean, while it may not seem like much, as our previous speaker said, you can hardly feel a degree and a half. That's not a big deal. I mean, we can just go and turn our thermostat a little bit and we can correct for whatever heating there's been outside. However, to the ice, small increases in temperature make a big difference, especially if you go from having an ocean that's colder than the ice that's in contact with it to an ocean that's warmer than the ice it's in contact with. And the glaciers that are most at risk are the ones that are in contact with the ocean. Those are called outlet glaciers. In addition to glacial ice melting and causing sea level rise, along with the thermal expansion that we already talked about, we also have the potential to melt permafrost, which is permanently frozen soil all around the Arctic Ocean, and much of that is underwater on the continental shelves, particularly the shelves north of eastern Siberia, and to a lesser extent off of Alaska and Canada. And so when that permafrost, which is essentially freshwater ice, comes in contact with warm seawater, then it melts, and that is beginning to occur at an accelerating pace. So this is a diagram from the IPCC, essentially showing where the heat has gone in the ocean since 1970, and the two stripes, it's like pieces of pie. The upper one is the upper ocean, the upper 700 meters of the ocean. The darker blue color is the deeper ocean between 700 meters and mostly 2,000 meters, but some data from below that. And then you can see a couple of little tiny slices of pie in the back and the bottom there. There's ice, which is given in the light color there. And then we have the land warming, which is what we heard about in the last talk. And then there's this little tiny sliver at the bottom, which is the amount of heat that's stored in the atmosphere. And of course, that happens to be small because air has very little heat capacity compared to water. So it's not a surprise that that should be warming, or essentially storing very little heat. And so here is a diagram from Woods Hole Oceanographic, a school that I got a joint degree from with MIT. And you can see there's warm water coming up from the south, and it's been colored to indicate the degree of warmth. And essentially a portion of the water which circulates around the Great North Atlantic Gyre peels off and comes north essentially to feed into the higher latitudes. And so you see a branch going up, the Norwegian Atlantic Current going up the coast of Norway. Some of it gets into the Barents Sea where that little star is. Some of it cools and sinks and becomes part of the general thermohaline circulation. Part of it peels off near Iceland as the Imminger Current goes around Cape Farewell in southern Greenland and up into the Davis Strait on the west side of Greenland. And so there's a little triangle there at Jakobshavn Fjord, which I'm going to show you some pictures and some data from in a bit. So this is some old history. This is a diagram from Fridtjof Nansen's crossing of Greenland. In his day, in 1888, he planned an expedition essentially to walk across Greenland. Before satellites and airplanes, people had no idea what was in the middle of Greenland, and essentially he proved that there is a big ice sheet that's continuous across Greenland, and he established the ice summit. But before he could get to Greenland to do his walk, he had to deal with the East Greenland Current, which was carrying pack ice that was 30 to 40 feet thick. That's what it was like in 1888, 30 to 40 feet thick. I mean, it's in the order, the thickness of this, the height of this room. Serious ice, and it was a hair-raising expedition in 2 small boats, and they managed to finally get across in about a month's time through this narrow belt of heavy-duty ice. And in the process along the coast of Greenland, Nansen found the crushed wreckage of an American ship called the Jeannette, which had been crushed in the New Siberian Islands. And he knew when it had been crushed, he knew how long it had been since it had crushed and where it came from, and he correctly surmised there must be a current system that carries the ice across the Arctic Ocean and was responsible for depositing the ship, and he decided he would try to ride that ice essentially with an ice-strengthened ship called the Fram. Now, this is a cover from a data report from an expedition. This was the last of 3 Arctic expeditions I made in '88, and essentially in that time, the sea ice was 3 to 5 meters thick. So a significant change in thickness from Nansen's time. And today we have in the order of 2 or 3 meters or 3 to 6 feet of ice, but there's increasing areas of open water which reduce the albedo of the Arctic Ocean, which has traditionally reflected most of the sunlight back into space rather than absorbing it in the ocean water. So we're warming water in the Arctic as well as importing warm water from lower latitudes. So this is a more quantitative estimate of the kind of transport that we're getting. These numbers are in spheredrips, which are equal to 1 million cubic meters of flow per second. A little hard to get your hands around something like that. that is equivalent to the sum of all the freshwater rivers in the world combined, one Sverdrup. So these ocean units are big compared to river units. And so there is 3.1 Sverdrups entering the Barents Sea, 2 Sverdrups going north of Spitsbergen, and you can clearly see the transpolar drift stream given in those large arrows. And then there's some material. It turns out that the Florida current has an average of 32 Sverdrups, and so the amount of warm water coming north is in the order of a quarter of the strength of the Gulf Stream. It's not as strong as the Gulf Stream as it goes through the Straits of Florida. That's properly called the Florida current. So this is me on the left and Humberto Guarin, Colombian, and we are standing next to an igloo we built. And it turns out that this particular year in 1988, there was an extraordinary storm that occurred because of open water in the Barents Sea. That warm water that adds to the Barents Sea melted a big hole through the ice cover about the size of one of the Great Lakes. And to have a source of heat and moisture in near proximity to cold pack ice spawned a hurricane-strength storm that blew for 2 days, including a tremendous amount of snow. Sort of like you hear about lake effect snow on the Weather Channel. This is ocean effect snow. And so we got 3 feet on the level ground. This blew for 2 days. The people on the ship, many of the Norwegian crew, had been in the ice for 30 and 35 years, and their fathers and their grandfathers and their great-grandfathers before them had been in the ice, and there was no knowledge of a winter storm of this magnitude. And you may be aware or not aware that hurricanes and other strong cyclonic storms cause upwelling of water from below. And in our latitude, that water tends to be colder as you get deeper. And essentially, if a hurricane goes stationary, it can pull the thermocline up to the surface, and you can get a patch of cold water that's brought to the surface, and that can reduce the intensity of the storm. This is just the opposite, because that deep layer in the Arctic gets warmer because of this Atlantic water that comes north. It comes north, and then it slides under the pack ice, and so there's a layer a couple of hundred meters down that is a couple of hundred meters thick now and has temperatures of 1, 2, and 3 degrees, depending on where you are. That's plus degrees. And so when you bring that in contact with sea ice, it melts it from the bottom. So this layer of snow sat for about 2 weeks before this picture was taken, and it turns into a lightweight solid, which is perfect for making igloos. That's the good news. The bad news, of course, is it insulates the surface of the pack ice. It's tremendous insulation. You can live in an igloo made of this material, and you can live essentially naked in it, as the Eskimos did. And just the heat of your body is enough to warm the inside of the igloo. So incredible efficiency, but it also insulates the surface. So when you bring warm Atlantic water up into contact with the base of the sea ice, it begins to melt. So this is, I built automatic profiling devices, early robots called cyclosons that went up and down along a taut wire, essentially measuring temperature, salinity, currents, whatever sensors you put on them. And essentially, so I had a bottom stop set here for 150 meters, and the top stop was the ice effectively. I had to remove 23 tons of ice to make the hole to put this instrument through by hand. That's what you might call Christian work. So it's an amazing thing to see that thickness of ice. I know it was 5 meters thick where I dug it, because I pulled that ice out a piece at a time. And here I am waiting for the cycloson to come back up in this hole inside of a heated shed. And so it turns out that you had to keep the ice from regrowing in there. There's actually a seal who started using our breathing hole. as one of the few places he could catch a breath. And this is a cyclotron discharging helium, and it's about to make a downward profile. So, and this is the sample of the data taken from this, showing the temperature below the surface. And as you can see, there's a major influx of warm water from below. The mixed layer is in the order of minus 1.2 degrees C. The melting point for sea ice is about minus 1.8. So it may not seem like a very big difference, but the sea ice was melting from below. And this was a shock to the people, the Norwegians. There was a young PhD candidate from University of Washington who come to measure the growth in sea ice in the wintertime. That was the conventional wisdom. It got cold and the ice gets thicker, right? Well, not exactly. So if pack ice could melt when the atmospheric temperatures were minus 40 in the Arctic winter, near 84 degrees north latitude, that's 6 degrees short of the North Pole, I was convinced this was pretty convincing evidence for global warming having arrived. And I also knew that the waterfront home I had recently purchased in Miami would be at risk, increasing risk from rising sea level. And the question was, you know, how fast? Not that we wouldn't be in risk or not, but when would this likely occur? So this is a picture. We were pushed out of the transpolar drift stream by that storm, and it pushed us down through the Straits of Katoya, and we saw some amazing ice pressure, and basically the heavy-duty pack ice broke up as we were thrust down into the Barents Sea. And so this shows ice breaking up, and you can see the amount of poles sticking out is 12 feet. You can see approximately where the snow ice line is, sort of halfway to the water surface, which is black, and essentially below that we have in the order of 5 or 6 meters of sea ice. And so this is thicker ice than you see in the Arctic Ocean today. And this is an average monthly sea ice extent for July from 1979 to 2014. And as you can see, there is a downward trend in sea ice extent. More important probably is the sea ice volume. And the upper series of curves, there are some light curves which are essentially independent outputs from a number of IPCC sea ice models. The darker curve is essentially the consensus of the models, and then the curve below is the best estimate of what we're observing in sea ice volume. And as you can see, the IPCC models show sea ice going forward to 2100. The best estimate of the current sea ice volume shows a different story. This is perhaps another way to more clearly look at this. This shows the radial lines are essentially years starting from 1979 when we began to get satellite data to 2014, and it shows each one of those figures is a monthly figure. The one that's closest to the center is essentially September, which is the customary minimum ice extent in the Arctic. And as you can see, it's spiraling in toward zero. The other concern with ice in the Arctic is permafrost. And permafrost is permanently frozen soil, which contains large amounts of frozen organic matter and methane hydrates, which is a form of methane associated with water ice to form something of a cage. Permafrost covers about 22% of the land area of the northern hemisphere, but of particular interest is the area shown in the speckled color, and essentially that is the underwater permafrost. During the last glaciation, sea level was about 400 feet lower than it is today, and so the continental shelves of the world were largely exposed to the atmosphere. And some of the continental shelves were glaciated, but the ones north of Siberia were not, and the ones north of Alaska were not glaciated. So they were subject to freezing. And so there's an immense amount of permafrost that's subsea. And so the area in East Siberia also happens to be very shallow continental shelf area. So the warm water we've got in the Arctic Ocean, both from importation by currents and from local heating, is essentially working on melting that ice. So this is a cross-section of permafrost going northward from Anchorage and that area, coastal Alaska, through Fairbanks and up to Perto Bay, Point Barrow, and Resolute, essentially at the Arctic Ocean. And what you can see is the thickness of the permafrost increases dramatically as you get further north. And so once you get north of the Brooks Range, you're on the north slope of Alaska, and that's a big layer cake of permafrost deposited by layer with bits of tundra between it. The active layer melts and freezes every year, and the surface skin of it is tundra, which is a assemblage of plants and dwarf shrubs and trees, which is about so thick it looks like sod you might buy at Home Depot, except it's miniature plants that you might be familiar with further south. And then it refreezes every year. The permafrost tends to grow when conditions are cold enough in the winter, but it's gradually warming. So I'm not going to show you all the data from the different permafrost wells that have been drilled up through Alaska, but it's clearly warming by the order of a degree C compared to the earlier 1979 data. So tundra and boreal forest fires can melt deep holes in permafrost, exposing the edges to accelerated melting in succeeding summers. Like a rapid shoreline meltback that I'll show you from Barrow, these growing scars are called thermal karst features. And it's much more difficult to melt the permafrost from the top down than it is melting the sides of it. So these scar features make a significant difference. This is a aerial photograph of Point Barrow, the very tip of it. This is the northernmost point in the North American continent. It's a gravel spit barrier island which is assaulted by sea ice in winter and by waves from midsummer till the Arctic Ocean freezes up again in now December or January. It used to freeze up in October, but the freeze up date keeps getting later and later in the year as the residual heat in the Arctic Ocean has increased. So this is a picture of a cliff top in Barrow. This is a place, the guy at the top is essentially looking for ice wedges in the permafrost pattern, and essentially you have a layer of tundra overhanging the top. This is a picture made at midnight, and essentially at midnight the sun is shining from the north in Point Barrow. A little odd to get your head around, but it's melting so fast you can actually see material just sloughing off the cliff, just constant sloughing down, and just, you know, it's just the sound of melting is everywhere. And so Bill was trying to find that ice wedge, and he felt on the underside of the permafrost or the underside of the tundra where it joins the permafrost, and this boot sole fell out of the bottom of the permafrost. The village where this boot sole was found, about 2,000 years old. I don't know for a fact whether this boot sole is 2,000 years old, but it very well could be. It's been in cold storage, and I notified the Heritage Center of the find, told them where to find it, so if they would like to collect it. So this shows a picture of the coast of Barrow, again from the air, and what you can see here is that the area where most of the village is located has been reinforced to slow down the erosion process. But there's an ancient village that dates back about 2,000 years to biblical times, which has a series of sod houses in it, which is essentially being lost due to coastal erosion. And this is common throughout the Arctic. In fact, Barrow is one of the coldest places left. You can still store meat in ice cellars there, but anywhere else, the ice cellars are beginning to fill with meltwater, and so they don't have their free cold storage that they had for so many years. And most of the places where the Inuit have chosen to live are delta regions where food is abundant. There are salmon runs and Arctic char runs, and so this Point Barrow is just one of a large number, one of the bigger ones, a very successful place because there's annual whale migration, and they have permission from the International Whaling Commission to catch whales. So this is one of the things that is most concerning to me. It turns out that the methane that's essentially being exuded on the East Siberian shelf is pretty stunning. And if you physically go there, you can actually see the methane bubbling up. We no longer have to produce the methane. The heat in the ocean is melting the surface of the permafrost underwater, and essentially that is accelerating the process. In addition, we are now getting Arctic fires that have been started by lightning in dry tundra or boreal forests. These were once rare, but now as the atmosphere has warmed up, you actually get thunderstorms in the Arctic where they were unknown before. It wasn't an Inuit word for thunder. And they didn't need to talk about rain very much either in the old days. Now you get rain in the north and into Greenland in every month of the year. One of the effects of having these increasing open water areas is you get persistent, strong cyclonic storms, which can persist for a week or two in the Arctic Ocean. And those Arctic storms are capable of moving sea ice, especially as the Arctic Ocean is no longer frozen solid. There's a lot of open water, so it's easy to push it around. And you don't necessarily have to melt it in place in the Arctic. You can essentially transport it out of the Arctic. So the picture on the right shows transport going out through the East Greenland Current along the coast east coast of Greenland. So these persistent storms create surface gravity waves. And it turns out that sea ice is very brittle and it breaks like glass. And so if you flex it with surface gravity waves, a big swell running under sea ice, in just a matter of minutes will start to shatter the sea ice. And the size of the ice flows that you generate depends on the wavelength of the swells. And so the preferred size of the ice flows is about half a wavelength. And so you're essentially flexing the ice. Ice is extremely strong in compression. You can't break it easily with compressive forces, but tension, it breaks like glass. So imagine taking a piece of chalk over your fingers. You can snap it easily because chalk is also very strong in compression, but not very strong in tension. So this warm Atlantic water, of course, is being upwelled by these persistent storms. So it can go to work on the remaining pack ice. Other effects, it turns out that starting in the summer of 2010, the Northwest Passage was opened for navigation. And the Coast Guard station in Point Barrow was shocked to see a German cruise ship off their coast requesting permission to anchor. And they couldn't imagine where that vessel had come through. And the captain said, well, yes, we just came through the Northwest Passage. It's now open for business. And also the northern seaway along the Siberian coast is open a long time. In 2010, there were two competing groups essentially sailing in boats circumnavigating the Arctic Ocean, essentially along the coastal Polinias and through the Northwest Passage. So this is a photograph I took in 2010 from an aircraft going to Ilulissat in Greenland, and the surface of the East Greenland current shows about 1/10 sea ice cover seen from 30,000 feet. Almost no multi-year flows, that is ice flows that had grown over more than one season, were to be seen from the air, and where Nansen had fought for a month to cross 20 kilometers. 25 years ago, I had seen 9/10 ice coverage dominated by heavy multi-year ice. That is no more. So now to talk a little bit about glacial ice. This is a polar projection of what the Earth looked like about 21,000 years ago at the peak of the last ice age. And essentially you can see large parts of North America were covered with glacial ice, in some places a mile or even 2 miles thick. Northern areas in Europe were covered. Greenland was totally ice covered, and it not only covered what we think of as the continents, but it also went out onto the continental shelves. So Long Island is a pile of gravel and sand that was pushed there by a glacier, what's called a moraine, a terminal moraine. And Cape Cod is also a terminal moraine. So those are left by the ice as it retreated. So the Ilulissat, which is an Inuit settlement, shown where that triangle is where I'm going to show you some photographs of what these things essentially look like. And you'll also notice that the continental shelves in eastern Siberia are not glaciated, and nor are the ones in Alaska. There simply wasn't enough moisture available to build up the glacial ice in those areas. And this is, I took a trip up the Hudson, and this is looking at the Hudson River Valley near Franklin Roosevelt's Hyde Park, New York home. And you can see the clear evidence of glacial striations in the rocks along the edge here. So glaciers tear rock off of rocky surfaces and use it like aggregate from sandpaper, and they gouge the underlying rocks. If you have a mile of ice, the pressure is almost unimaginably large, and so you can force one rock through another. So you can make grooves in the rock in some places a foot deep because of the kind of pressure that you have. And so the Hudson River looked like Jakobshavn at the end of the last ice age, perhaps 15,000 years before present. So this is a picture of the Greenland ice cap, a map showing the remaining continental scale ice sheets. There's only 1.7 million square kilometers left out of the 30 we had at the peak of the last glaciation. The ice dome summit in east central Greenland is 2 miles high, and the glaciers cover about 81% of Greenland today, and the weight of the ice depresses central Greenland about 800 meters, and it's largely below sea level. And one of the real dangers for rapid ice melt is to have the base of the ice below sea level, because it means if the warm ocean melts into that, essentially it can continue to excavate the ice by melting. Note the scientific sites. That summit site up in central Greenland is where they got the longest ice cores. Those go back about 450,000 years. You can go back over 800,000 years if you go to deep ice in Antarctica. So we can know what the climate has been by the data from the air and other materials in the ice cores. Now, in recent times, there was noticed around the turn of the century that there were earthquakes coming from around the coast of Greenland in places that they had never seen earthquakes in the seismic record. And so they correlated that, Holland et al. With the increase in melting at the Jakobshavn Glacier. And like many of these geological things, you name the effect for the place it was first observed. And so Jakobshavn was the first place that they hypothesized this, and the sudden increase in subsurface ocean temperatures in '97 along the entire west coast of Greenland was correlated with the onset of these seismic activities. You can see on this picture where Ilulissat is. You can see the path that the icebergs tend to take up into the Davis Strait and then down along the coast of Labrador and Newfoundland. And you can see the place where the iceberg was that the Titanic ran into during its ill-fated voyage. You can also see the places where other icebergs have been, and you can see in the early parts of the 1900s and the late 1800s, there were some very big icebergs that survived fairly far south, down to the Azores even. This looks like spaghetti on a plate. The diagram on the left side here shows temperature on the horizontal axis. Vertical axis is depth in meters. This line is the freezing temperature or melting temperature for freshwater ice. And this is the average. This thicker line is the average of the temperatures near the outlet of the ice stream in Jakobshavn before the warm water got there, and the accentuated one to the right shows that the water has warmed up about a degree between these two cases. And that may not sound like much, but it is essentially doubling the melting potential of this water. And then on the right side, we have a similar diagram for salinity. This is the early record, and this is the later average, and it shows about a 1/10 of a part per thousand increase in salinity. So the water has both warmed and gotten saltier. And this is a vertical, downward photograph of the Jakobshavn Fjord. You can see the town of Ilulissat near the outlet of the glacier, and you can see the position of the calving face through time. They have records going back to 1850 here. The Danish people and the Norwegians were up here whaling and sealing and trading with the Inuit who are doing that. So this has a very long history, and you can see that there's a SETI regression or melting back, and the calving face is essentially going towards the east with time. And you can see in '97 there's a huge jump to 2004 when that warm water got there, and essentially this is continuing to melt. The calving face is significantly further inward, pretty much off the page here. And that calving face is not only retreating, it's retreating into accelerating ice supply. So the force of ice coming out of these fjords is pretty amazing, and the fjord is about 1 kilometer deep at the calving face in this case, and now it's deepened down to about 1.2 kilometers deep where the new calving face is going on. So this is one of those deepening inward fjords. There are a bunch of ancient river valleys that can be seen using ice penetrating radar, and essentially you can know what the topography of the rocks were. And so these deep old river valleys are the ones that deliver the warm water inland. And this is a picture from later showing the calving face from the air. There are surges in these in the Jakobshavn ice stream of as much as 3 kilometers in 90 minutes, sort of like squirting toothpaste out of a tube. And it's those big ice movements that give rise to the seismic signals that have been seen. This is the calving face retreated in 2011, and my colleague Hal Wanless was there in 2012 and 13, and it continues to follow those river valleys inward under the inland ice. And in fact, you can see places where the inland ice is collapsing into the ancient river valley, showing you that there's deep meltwater going in. Well, these are 184 earthquakes from 1993 to 2005, using a model of essentially an avalanche model. This is done by Cyan Ekstrom. And the places where those dots are, and if you look closely, many of them are on top of each other, repleted places. Those are the outlet glaciers where the warm ocean water is meeting the inland ice. And so these are commonly up to Richter 6 and 7. And so now you can study ice movement here in Florida by essentially having a feed of seismic data. You don't have to go to the ice to study it. The ice is talking to us, and we should listen. And so the next question is there something like this going on in Antarctica? And they found 14 similar seismically active sites in Antarctica. And they know it's the outlet glaciers because they've taken first the position of them, of these earthquakes, and then secondly, they put GPS receivers on the ice sheet and actually correlated the earthquake with the movement of the ice. Now, in the case of Antarctica, it's a continent, not an ocean, although large parts of what we think of as a continent are also under sea level. And so there are connections that are likely to develop if we continue melting our ice. And there's a stronger circumpolar wind field which is producing upwelling of warmer, saltier water to the edges of the fjords and the ice shelves in Antarctica. And this is what the ice looks like in Jakobshavn Fjord. As an oceanographer, I was thinking about bringing a ship in here to study the structure. You'd have to bring a ship in and by air and drop it on top of the ice. You couldn't possibly navigate one. You can take air expendable probes from a helicopter, perhaps. And this is a calving face of a much smaller glacier a little further north called Eki. And for scale, there's a cruise ship in the picture. Can you see the cruise ship? You know what cruise ships look like if you go down to South Beach. This one's not quite as large as some of the mega ships we have in South Florida, but it's a substantial ship. You can also see the trim line, which is an area above the ice, present ice surface, where the vegetation has been scrubbed off by ice in the past. And so you can see the thickness of ice that has been lost since that trim line was formed. And this is looking from the Arctic Hotel north of Ilulissat, and those are the icebergs that are stuck on the terminal moraine at the output of the Jakobshavn Fjord. And they look big from 4 kilometers away, and there's not a lot of ice that's on the outside, bergy ice in this picture. But the next year, there was a breakout of icebergs through that terminal moraine, and many more icebergs present. They actually had to push them around the little ones in order to get the tourist boat up to Eki. And you see the size of these icebergs. They're like islands, the size of Manhattan, that kind of thing, coming out there. And this is looking from the air. You can see the big bergs are essentially stuck on the bank, and they're damming up the smaller ice. This is called a melange. And this is my favorite iceberg. We call this one the Matterhorn. The summit of it is higher than a 50-story building. We estimated it from the land. And just amazing, and to think that most of this is underwater. This is the tip of the iceberg, as they say. Now, the warm, salty water that gets into the fjords has the effect of melting the base of these big bergs, and it releases fresh water, which is much less dense than the salt water that surrounds it. So it floats up to the surface. It also releases the trapped gas in these ancient pieces of ice, some of them hundreds of thousands of years old, and those bubbles essentially rise up too, so that increases the amount of buoyancy in that fluid, so there's a sheath of rising fluid along the edges of these bergs, which bring warm, in this case nutrient-rich water up to the surface. These fjords have been choice places to live for the Inuit because there's so much biological productivity. At the surface, the fresh water was flowing out at about 1/2 meter per second, and there was a compensating saltwater inflow at the base. And you can see here fragments of icebergs that have ground off on the ice bank, the terminal moraine. And you can see a clear front between the warmer, saltier water offshore and the cold, recently upwelled water with the chunks of ice in it. So, now we're going to come back to Miami. Close the loop. Remember I said I was wondering, when this sea level rise is going to arrive. And one of the reasons we in Miami should care about global warming is that sea level is rising because the ocean is expanding from the warming that we showed you in the second slide. But it's also rising because we're adding meltwater from these Greenland glaciers and the Antarctic glaciers. And we're also adding water that we have produced from aquifers on land and pumped into the ocean by means of evaporation off the land. So a number of things are contributing to this 3.4 millimeters per year that we have today. And this is my street. I'm essentially standing in my street here. And this is on October 28th, and this was the date in which Sandy was passing offshore. We didn't get the effects of Sandy. You can see there's no strong wind ruffling on the surface. You can tell the date because there's a Romney sign. Romney, you might remember, in the Republican convention mocked Obama for wanting to slow down sea level rise, thought that was a big joke. Doesn't seem like so much of a joke to me. In fact, the Miami chapter of 350.org calls themselves, their motto is sea level rise is no joke. So what was giving rise to that? Well, there was a number of things that were going on. The sea level rise that we've talked about is going on. The blue line is essentially the forecast for tidal elevation in Miami tide gauge, which is at the Rosenstiel School dock. The actual surface elevation was running nearly 1.5 feet higher than that, shown by the red symbols that are all clustered together to make that upper curve. And then the green is essentially the difference between the two, showing an increase. So we had nearly 1.5 feet more sea level rise than was forecast, and this is already a king tide. So a little bit of misfortune in our getting this event at the same time. Well, what was happening, turns out that the Florida current runs through the Straits of Florida all the time. It's usually around 32 spheredrips, and sea level in the Bahamas is about 3 feet higher than it is in Miami as a result of that, because the Coriolis force wants to turn the water to the right in the northern hemisphere, so it wants to drive it up onto the Bahama banks. And so there's a sloping sea surface which provides the countervailing pressure gradient. And so we have a cable that measures the transport of the Straits of Florida, and at this particular time the cable was not saying 32, it was saying 17, which is almost half of what you expect it to be. And so it was not holding back as much of the water from the Sargasso Sea as it would normally do, and so we had nearly 1.5 feet of additional sea level rise. And so this gave the additional inundation. So this is the future. These are the forecasts by the Miami-Dade 4-county climate compact. Miami-Dade, Broward, Palm Beach, and Monroe counties have decided that they were going to consolidate on one sea level rise estimation so that we aren't telling the people we're applying for money from the federal government different answers. You got to speak with one voice, and this is a consensus. A little bit of an interesting discussion involved with this whole thing. You see the blue area in the middle. That is supposed to be the most likely zone in which sea level rise is going to be. But the actual answer depends on what we do as a civilization and as humanity. Do we get serious about reducing CO2 emissions, or don't we? That's the question. So in the past, IPCC has given a high, low, and a medium forecast for sea level rise, and typically the actual observed sea level rise after the fact runs at or above the maximum projections. So if we follow the same trajectory in the future, we're likely to follow the top the 2-meter curve in 2100, a so-called NOAA high projection. The one down at the bottom, the dashed curve at the bottom, requires rapid reductions in CO2 emissions in order to get that curve. And the consensus of the group meeting was that it was so unlikely that we were going to get serious about reducing CO2 emissions that that was not likely to happen. This report is available on the Broward County website, which references this data. So in order to get this lower curve, we would have to reduce our emissions dramatically. And the consensus of the committee was that there's not that much evidence that the humans on Earth are doing that. And so they thought it was so improbable that they presented it as a dashed line. So in the Arctic, there are 3 different emerging forms of convection. You may be familiar with convection on a stove. If you put a pot of cold water on the stove and you heat it from the bottom, it turns over because you're heating it. You're creating buoyant water at the bottom of the pot. It wants to float up, and the colder water at the top sinks down and it overturns. That's called convection. You have convection ovens which stir things. Well, this is convection by natural causes. One form of convection we just talked about is the melting of the fabric of the submerged permafrost on the Arctic continental shelves, which releases both buoyant fresh water from ice melt and also buoyant methane bubbles. And so that is essentially floating up to the surface. That brings in more water in contact with the permafrost. So it's a convective system driven by the melting process. A second type of convection that's going on, you don't hear about, is the glacial ice in the deep fjords is releasing fresh water at depth. It's highly buoyant compared to the salt water, so it wants to flow upward. And when we release these mass numbers of microscopic bubbles, they want to float upward too. And so you have natural convection there, which brings in more warm, dense water into the fjord, which releases more. So it's like this reinforcing feedback is natural convection. And it's dramatic to fly inward in a helicopter over these ancient valleys and see a swale where the ice has collapsed perhaps 500 or 1,000 feet into these ancient valleys because of the warm water from the bottom. And then the last one is the new arrival of thunderstorm convection in the Arctic with attendant lightning, and lightning can spark boreal forest fires and tundra fires that form these thermal harsh scars, and they also provide an abundant source of soot and poorly burned material, just like the cooking fires in India, and some of that ends up on snow, ends up on the top of Greenland. So if you want to learn something about the science of it and the policy, here are a couple of good references. The one on the left is by Richard Alley, Earth, the Operator's Manual. It's part of a PBS 3-part show. And on the right, we have Storms of Our Grandchildren, a book by Hansen, which is a very clear exposition of the science of climate change. If you want to look into issues of the surprising progress that's been made to the transition between fossil fuel and renewables, this book, The Great Transition, is a great source. It shows that more than half our new generation capacity in the United States is renewables, and it shows the terrific project. Can you imagine that 10% of the electric power in Texas is being made from wind? Would you have ever believed that in the land of oil and oil companies? Well, they make so much wind power in Texas at night that they give it away free. So if you have an electric car in Texas, that's a good deal. You pay more during the day because obviously the power company has to make a profit. And this is a book the last book by Hermann Scheer, great energy student in Germany and the architect of Germany's effective Green Party policies. And then if you want to push for divestment of fossil fuel stocks and you want to do protests, 350.org is a good group to get involved with. They were part of the support for the climate march in Miami. That got very little publicity. And if you want to exercise your democracy muscle, if you actually want to interact with your representatives and your senators, I can recommend no group higher than Citizens Climate Lobby. There are 24,000 of us at the present time. We go to Washington and every year and lobby hundreds of times. And well, that's it.